Alright folks, let's continue. I can see a couple of new faces in the audience. You can see the previous lectures of this module on YouTube if you follow the links from the blackboard. So after each lecture, and there it says videos, here videos for this video at any point, including the time when you're preparing for the exams. Okay, so a lot less boring things today compared to the two previous lectures where we were dealing with formalities and definitions. We will look today at a relationship between physics and mathematics in terms of which functions physics does and does not permit as solutions to its various series and equations. Mathematics is the study of functions, so arbitrary things are permitted there. But as you will see by the end of today's lecture, only rather few of those things physics allows for various reasons that have to do with the available energy, the available force, the total possible concentration of the substance in the sample. These are the various conditions that are imposed by physical reality on what mathematics would otherwise view as an infinity of possibilities. So before we start, again a couple of definitions, and the first one that we need to introduce is the definition of a discontinuity. Informally, on the hand-waving level, a discontinuity is an abrupt change in a function from one point to the next. If we plot some function f of x, or perhaps of time, so for a time-dependent trajectory of some particle, and let's say it moves somehow and then just abruptly jumps from one point to another, and then goes on further. So perhaps this is some kind of coordinate. Let's call this x plus. And so let's call this point t0, and you can see that the particle smoothly changes its coordinate, then jumps, and then continues smoothly changing its coordinate. If we look at this function in some detail, in particular if we would like to find out the limit of this function at t0, we would have a difficulty because if we approach this point from the left, we will have one limit at that point, and if we approach it from the right, we will have a different limit, and that is in fact the formal mathematical definition of a discontinuity. So we will introduce something called the left limit. Lim t goes to t0 from the direction of minus infinity, so t minus of x of t. So let's call this x1, point here, x1 and that x2. So the limit as we are approaching the discontinuity from the left is x1, left limit, and the limit as we are approaching from the direction of plus infinity, hence the plus in there, so limit t to 0 from the plus direction, x of t is x2. And the definition of a discontinuity is when the left limit is not equal to the right limit. Lim t to t0 minus x of t is not equal to lim t to t0 plus x. And this is just so much formality for now, so this is continuity. But let us now go into the actual physics of the matter. Let us consider what it actually takes for a particle to jump position like this instantaneously. For that we would need to go into kinematics, right? Calculate velocities and accelerations. But as you know from your school physics course, velocity is the derivative of the coordinate. But we have a function that's broken up, it's discontinuous. We don't know how to differentiate this at this point. So what we will make use of today is the limits that we have introduced in the previous lecture. I will introduce a discontinuous function as a limit of continuous functions. So let me illustrate what I mean. Let us consider the velocity of the coordinate first as the following function. 1 over 1 plus e minus kt, where k is some positive number. Let us try plotting this function and seeing what is going on. So this will be our coordinate, x, and that will be time. When t is at minus infinity, so when t is there somewhere, we have plus infinity here. The denominator is very large. This function is 0. So it begins, so let's say we put time equals 0 here. But the function starts its life at 0, like that. Then as time approaches 0, when t is 0, this exponential is 1, and so we have 1/2. So at some point, function will rise to 1/2 at exactly time equals 0. Something like that. Closer to 1/2 here. And then as time goes to plus infinity, this exponential vanishes because it's the exponential to minus infinity. It's a very small number. And so we will have 1. So at some point it goes to 1. And then just approaches it. That number is 1, and that is 1. Let's now think what is going to happen if we make this number k larger and larger. Well, the sharpness of the function will change, because if k is really small, this transition will happen slowly. If k is really large, this transition will happen fast. So if we make k a bit larger, what is going to happen is we will have a function that does this. So it does exactly the same, but faster. And ultimately, when we increase k to a really large number, as if we take the limit, what is going to happen is this function will abruptly jump. So there will be trajectory, and it will just abruptly jump all the way up here, and we will have effectively the discontinuity that we require. So this is k small. That is k large. And yellow is k infinite. And so you can see that to make ourselves a discontinuity, what we need to do is to take the limit with respect to k. And this is why I have left so much space. Limit to infinity. That is our function. We treat the discontinuity as a limit of continuous functions. Well, what this permits us to do, of course, is to differentiate, because this limit is finite, and so what we can do is we can just differentiate this with respect to t and see what is going to happen. Okay, so our velocity as a function of time is x prime with respect to time, and that will be the limit k owing to infinity of the time derivative of this. Well, as you well remember from school, when we have the derivative of a ratio, it's numerator times denominator prime, so it's 1 plus e to the minus t minus denominator prime, numerator times denominator prime, and denominator times the numerator prime, but numerator prime is 0, so that is 0, divided by the denominator squared. 1 plus e minus kt squared. Okay. What we will now have is a certain simplification, so the derivative of this Derivative of 1 is 0. Derivative of e minus kt is minus ke minus kt. I think I've swapped them around, so there should be minus and there should be the plus. So we have limit k to infinity of e to the minus kt over 1 plus e minus kt squared. So far, so good. Let us calculate this limit at the point where our event happens. So we will put time to 0. Our velocity at 0 is limit k going to infinity of. Well, if we put time to 0 in here, the exponential of a 0 is 1. Here it is 1 as well, so 1 plus 1 squared is 4. And in the numerator we have just k, so this is k over 4. Now clearly the limit of k going to infinity of this is also infinity, which rings the alarm bells because we have infinite velocity. Well, what's the problem with having infinite velocity? Of course, the energy, the kinetic energy that we also remember from school was mv squared over 2, where m is the mass of the particle. Unless you have a photon, which has an well, basically zero mass, zero rest mass, infinite velocity implies infinite energy, and this is something we simply don't have in our chemical system. And so it turns out that it's not mathematics that prevents such trajectories from being possible. Mathematics is perfectly fine with these limits. It's the physical reality where infinite energy is not available. Okay, you thought jumping it from one point to another infinitely quickly is perhaps an overkill. Let's consider a milder example. Let us perhaps look at a particle that turns a corner sharply. So the profile of the coordinate will not involve any infinite jumps, but it will involve a sharp corner being turned. So what we'll do is this. Our time, this is our x as a function of time, and what we will do at time 0 is we will do the following. Suddenly, it will start moving. So it was sitting there, twiddling its thumbs, and then it suddenly decided to start moving. There is no discontinuity here. Again, there are no single function closed form analytical expressions for a function turning a sharp corner. So what we will do is we will again construct a limit approximation to it. We will take a look at the function that first does this. Does it smoothly. And then as a function of some parameter, when you make that parameter larger, it will do it slightly sharper. And then eventually, as that parameter goes to infinity, it turns into a sharp corner. So we would want some k. Alright, so very large. And then the white curve will be k going to infinity. It takes a bit of looking through the literature to identify a function like that. It's not anything that one can, of course, just guess. But I will just simply write that function down, and you can confirm by plotting on your calculator or a computer that this is what it actually does. So we will have, let's call this y. It's very good to distinguish it from the previous case, moving perpendicular. Okay, so y of t will be 1 over k log 1 plus e to the kt. That is actually a function that does this. Okay, what we can do now, of course, is we can differentiate it and find out what the velocity is and what is the acceleration. So let us do that, and moreover, let us take the limit as well. So our y of t would be the limit of k going to infinity. Okay, so the velocity in the direction y would be the derivative of this, and why don't we just take that derivative? So the velocity in the direction y of t would be limit k going to infinity of 1 over k log 1 plus e kt and then prime. Well, we all know how to take derivatives with respect to time. 1 over k is a constant. I will take it out of the bracket, and from there we just have a chain rule. So we have the outer function, that's the log, and then the inner function is 1 plus the exponential. Derivative of the log is 1 over derivative of the exponential, we know, so let's just do it. Limit k going to infinity of 1 over k, and then derivative of the log is 1 over whatever occurs under it, 1 plus e kt, times the derivative of whatever occurs inside. One derivative is just 0, e to the kt derivative is k e to the kt. So k e to the kt. As you can see, k cancels. So we are left with is the limit k to infinity of e to the kt 1 plus e to the kt. If we plot this function, let us see what we have here. You can probably guess it from this graph, in that that's time, that's the velocity in the direction y. If nothing was happening here, then the velocity would be 0, or if it just slowly picks up the velocity, so let's say that is after 0, nothing would be happening until this time 0, and then at some point the function decided to instantly acquire a constant velocity, so it will jump to some other value. So here we have a discontinuity not in the coordinate, but in the velocity. And of course, velocity was previously finite, and it is still finite after the jump. And so this is actually not a problem. We have one energy prior to the point, and then we have another energy after the point. So everything appears above board on the surface here. Energy considerations are past. Let us, however, look at the acceleration, which, as you know, is the second derivative of the coordinate, or equivalent is the first derivative of the velocity. So a in the direction of y t is, as you know from school, velocity prime of t in the same direction. So we need to take another derivative. So the limit of k going to infinity of that stuff prime. So numerator prime times denominator k e to the k equal 1 plus e t minus 1. Denominator prime times the numerator. Denominator prime is k e to the t times the numerator e to the 2kt. Two of them, divided by the denominator squared. 1 plus e to the kt squared. Let me check if I've not made any arithmetical mistakes in there. And that seems to be okay. And let us now simplify this. That is a limit to infinity of kx and x with a plus, kx and x with a minus. These two cancel. We are only left with this little bit. So k e to the kt divided by denominator remains unchanged. Okay, and we are specifically interested in the acceleration at time 0. So our a of y of 0 is a limit k to infinity. If we put time to 0, this exponential is 1, this exponential is 1, 1 plus 1, 2 squared becomes 4. Okay, so 4 in much the same way as we originally had there. And of course the limit k goes to infinity of k over 4 is infinity. So the velocity is finite and the energy is finite. What is infinite in this case is acceleration. So infinite acceleration, which is still a problem because of Newton's second law, where F was ma. Infinite acceleration of an object of a finite mass implies infinite force, which we don't have. So previously, we didn't have enough energy. Now we don't have enough, perhaps, materials to execute an infinite force on the object because any material will disintegrate. So you can see how physics plays together with mathematics here and how all the limits that I taught you in the previous lecture are becoming useful. So in general, as you can now see, there are functions that are admissible on physical grounds and there are functions that are not admissible. This leads to the concept of a well-behaved function. This is actually official, right? So even in very serious theoretical physics textbooks and occasionally mathematics textbooks, you will encounter sentences to the effect, let us assume that a particular function is well-behaved. Well-behaved means that it's admissible as a solution to some physical equations of motion. And what this means, definitions can vary. It is still semi-unofficial when you are looking at a paper, for example, academic paper that refers to well-behaved functions. It will always define somewhere what exactly it means by a well-behaved function. But for our purposes here, this means that the function itself and all of its derivatives are continuous. So f of t and all derivatives continuous, meaning they have no discontinuities. Okay, let us now actually define rigorously what we mean by continuous. And this is the second item on our agenda. That's the definition, the formal definition of continuity. The function is called continuous in a certain point if it's equal to its limit, both left and the right. So f of x is continuous in x naught if the limit x going to x naught f of x from the left is equal to the limit f of x going to x naught from the right, and that is equal to the value of the function itself at that point. And we will go through a few examples now of continuous and discontinuous functions. So let us begin with the ones that are continuous, so we can demonstrate that y of x equals x plus 1 is continuous in x equals 3. That's kind of obvious, right? It's a linear function, it has no special points, but we can formally say that indeed the limit of x going to 3 of x plus 1 is 4 from either left or right, and indeed y of 3 is also 4, and so the formal definition is satisfied. That's an obvious case, but there are cases that are a lot less obvious than this. Let's look at the function that is not continuous. If we look at y of x equals 1 over x minus 3 at the same point, then as you can see it's 1 over 0, so the limit is infinite, but the left limit and the right limit are different. If we plot this function, x and that's 1 of x around x equals 3. Let's see what happens when x is slightly smaller than 3. Well, the denominator is negative and very small, so we will go to minus infinity at that point. So it will be something like this. It's negative, and then it goes to minus infinity. And then if we are approaching 3 from the positive direction, the denominator is always positive, but it also goes to infinity. And so we have something like this. And so the left limit here is minus infinity, but the right limit is plus infinity. And the function has this abrupt jump, so it is clearly discontinuous at the point when x equals 3. There are a few exotic examples in mathematics. One function we've already actually indirectly looked at. I will give you 3. And they are famous because they have names. One is called step function. It's actually a heavy-side step function after a mathematician who studied it. And it has what's called a piecewise definition. This h of x is 1 when x is greater or equal to 0, and 0 when x is less than 0. So everywhere less than 0, it is 0, and then it abruptly makes a jump. So it's basically this. If we make that equal to 1, then it was 0, 0, 0, 0, 0, 0, and then it abruptly jumps. And this function is surprisingly common in physics, not as a solution, but as a stage setting. So well-behaved functions are not permitted as solutions, but they are permitted as conditions. For example, you can have an infinitely high wall through which the particle is not allowed to penetrate, or some such other condition that describes the reality around your system rather than the behavior of that system. Those are permitted to be idealized, and so heavy-side step function is encountered rather a lot. The second one is called signal, because it returns the sign of its argument. Signal. And it has the following notation. And as the name suggests, it is +1 when x is greater than 0, it is 0 when x is exactly 0, and it is -1 when x is less than 0. So you have it -1 as a strange punched out point in the middle, and then it jumps to +1. Neither function would be permissible as a trajectory of a particle, of course. And then there is a seriously exotic function, so Dirichlet's phase function, defined in the following way. D of x is 0 if x is irrational. For example, √2 that cannot be expressed as a fraction of 2 integers, and 1 if x is rational. For example, 2/3. Now, this is a very anomalous function, because if you think about it, there are rational numbers around each irrational number. You can approximate √2 arbitrarily close to this fraction. Decimal notation is an example of that. And around each rational number, there are irrational numbers. And so this was discontinuous at one point. This was discontinuous at one point. But this is discontinuous everywhere. It looks like dust. So there's a little bit of it at 0 and a little bit of it at 1 around everywhere that you can possibly look. We will not encounter this. This was a highly anomalous example that Dirichlet himself has invented to illustrate certain concepts in mathematics. Such a thing is unlikely, except as an approximation to describe any physical reality. Okay, so these are examples of continuous, discontinuous, and anomalous functions. And let us also do a bit more philosophy on the conditions that may or may not exist for integrals of functions. So we've so far focused on derivatives. But actually, in many cases, integrals also have conditions, so I will here further possible conditions. They are not always there, it depends on the problem, but you will encounter them as chemists. Let's consider, for example, a beaker with some concentration of some substance. As you know from basic physics, the total amount of substance here is the integral over concentration. So if we have this volume, E, then the total amount of, for example, sodium chloride present will be an integral over the volume of the beaker of the concentration of it of X or Z dV. There are certain conditions attached to this integral. We cannot have an infinite quantity of sodium chloride in the sample, and so this actually must be finite, so less than infinity. Although every year when students do their laboratory practicals, they do arrive at implausible answers. I think the funniest one I've ever seen was 22,000 moles per liter for glucose. So that was real sweet. And this is clearly a arithmetical error somewhere. Okay, so this cannot be infinite, nor in fact can it be negative, because you cannot pour a certain amount of sodium chloride to the universe, right? It really has to be positive. And so that's the first condition on that. And the second condition, it must be greater or equal to 0. And of course, the concentration itself as a function cannot be negative, except as a relative concentration, perhaps to some baseline level. So there are further conditions on the functions in the case of chemistry. Then there will be other things that you will encounter sooner or later. I will only give you the definition because the physical chemists will introduce quantum mechanics in due course, and if you attend the season 2 of this module in the second semester, I will introduce quantum mechanics properly. But there's a function there called the wave function that the second years present will be painfully aware of by now, and the first years must have seen it on the BBC somewhere. It's a very strange function because it contains in it everything that is in principle knowable about a physical system. Its complete past, its complete future, and its every conceivable property. It's kind of bizarre and unobvious that such a function should exist, but it does. And its absolute square, it's a complex function, its absolute square is probability density. It's the probability of the function being at point x at time t. Now, obviously, the sum total of all probabilities must be 1, otherwise something is seriously broken with the world, and that implies this condition. So, if we integrate over all space, the probability of it being there, it must always, no matter what, be equal to 1 at all points in time, so for any t. And because the coordinate extents are in principle infinite, that's an integral from minus infinity to infinity. So it's an integral over infinite extents of a function must nonetheless remain finite and be equal to 1. This is equivalent to saying that no matter where we look in the universe, a particle must be somewhere. And so the total integral probability must be 1. And so that's a different sort of condition. So I'd say I've given you the kinematic examples here that are we just walk through them in their entirety. But there are all sorts of other common sense conditions that various definitions of well-behaved functions might in principle involve. Okay, so another thing that we need to discuss is an important observation that solutions to equations, physical equations, must be well behaved. But the equations don't have to be. So equations might not be. I've already mentioned the situation where you've got the wall, hard walls that the particle cannot penetrate. But let me give you a couple of examples that you have already seen at school, but might not have thought about them as so utterly unphysical and unrealistic. So a good example is the electrostatic potential of R, and that's Q1, Q2 over 4 pi epsilon naught, 1 over R, where R is the distance between two charges, Q1 and Q2. Let's think about what this means. Right? You've all seen it. You've solved many problems as a GCSE physics examination. Let's think about what this means. This is the energy of interaction between 2 point charges. Let's start bringing them closer. Let's just, push them into one another. So we will have the limit of R going to 0. Nothing prevents us from just bringing them in contact. But of course you can see what is going to happen as R becomes larger and larger. This drops to 0, but as R becomes smaller and smaller, this goes to infinity. So actually the energy of 2 point charges that are in contact is infinite. Either plus infinity if they're of the same sign, or minus infinity if they're of the different sign. But of course the same applies to us looking at an individual charge, and let's just take a fine little knife and just cut it apart into 2 pieces, and then put them away from us. At the moment when you cut an elementary point charge into 2, this kicks in. And so actually the energy of a point charge is infinite. And so such a thing shouldn't exist in physics, and it clearly doesn't, right? Every source of charge that you have ever seen was either a charged atom, or a charged nucleon, like a proton, or electron, which cannot be perfectly localized. It's a probability cloud. So no actual realistic physical objects you ever encounter in practical reality when you start looking around is ever a point charge. However, a point charge is a very serviceable approximation, and you've been using it a lot in calculating, for example, ionization energies of the various atoms. So in the equations of motion, and we will see this a lot in Schrödinger's equation, first, second years have seen it already, such an object is fairly routine. However, in a solution to a physical problem, it's inadmissible because it would imply an infinite energy for a physical system. So there's a subtle philosophical difference in there. Don't go too deeply into it. I think this is, at the moment, just an illustration to the concept of these discontinuities, singularities, and so on. And this is, in fact, an example of what scientists call a singularity. A singularity is when a continuous function goes to infinity. And there are a few other examples of this. For example, gravitational potential. If you have 2 masses at a distance r, it will be m1, m2, over a bunch of fundamental constants. I don't really remember what those have been. Correct me if I'm wrong, there is some kind of gravitational constant in here. You may remember it better than I do, but it's 1 over r. And this actually brings us to the only exception to everything that I have so far told you. The one case where either a singularity exists in a solution to a physical theory and in fact in physical reality, or, which is more likely, that we simply don't know enough physics of what goes on inside, is a black hole. That is indeed the situation where gravitational collapse has brought enough matter close together for a solution to the general relativity equations describing that situation to become singular. And then it's a point mass, and it has a very steep gravitational potential, so steep in fact that the escape velocity exceeds the speed of light, and so, as you know from pop science, on the television, light cannot escape beyond a certain radius, and this is why this is called a black hole. And to my knowledge, that's the only example of a singular solution to a physical equation of motion that we can actually see in a telescope. But still, it's not entirely clear what's happening underneath this, what's called event horizon, so the radius from which the light cannot escape. It may not in the end be a singularity. There could be some force that's pushing back at the collapsing matter, and so it will still have a finite radius and therefore the finite energy as it should, because of course if you have the mass of the black hole, the rest mass energy of that thing cannot exist and exceed mc squared, which is clearly less than infinity. So the thing is probably actually non-singular. Okay, so the summary of today's lecture is under the guise of looking at the physics and chemistry of these things. I've actually introduced rather a lot of mathematics. So the formal definition of discontinuity of a function is when the left limit is not equal to the right limit. It's called a discontinuity. You have seen the discontinuous functions are clearly inadmissible, as for example trajectories. And in fact, if the function has a discontinuity in any of its derivatives, it's also inadmissible. And the function that is itself continuous and has all continuous derivatives is informally called well-behaved in physics. Many functions that occur in chemistry have further conditions of what constitutes a physically sensible solution. For a concentration has to be greater than 0, has to be finite everywhere. The integral has to be finite. For wave functions, they must integrate to strictly 1, and so there are other solutions that would have other conditions attached to them. The function is called continuous in mathematics formally if the left limit is equal to the right limit and it's equal to the value of the function at that point. We've seen an example of a continuous function and a discontinuous function that has a singularity at x equals 3 because it's continuous everywhere except 3, and at 3 it goes to plus or minus infinity, which happens to be the definition of the singularity. All of that applies to solutions, the real concentration profiles, real velocity profiles, real particle trajectories. If you look real closely at modern physics, you will see singular stuff in the equations that we are trying to solve. The most famous example being electrostatic and gravitational potential that actually have a singularity at the 0 distance. That's all I have to say.